For question number 31, it's given that a pair of dice, part A, so we are on question number 31, part A, and it's given that a pair of dice is thrown simultaneously, and if x denotes the absolute difference of numbers obtained on the pair of dice, then we have to find the probability distribution of x. Okay, this is a pair of dice, and let's say, so the total number of outcomes we know is 23 for a pair of dice, and total outcomes for a pair of dice is 36. And let's say this is our first die with the numbers 1, 2, 3, 4, 5, and 6. And the next one, the other die has the numbers 1, 2, 3, 4, 5, and 6. So our possible outcomes will be 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. This is 1, 2, 1, 3, 1, 4, and 1, 5. And this is 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. This is 1, 6. Similarly, it's 3, 2, 4, 2, 5, 2, and 6, 2. And this is 3, 3, 4, 3, 5, 3, and 6, 3. This is 4, 4, 4, 5, 4, 6. Okay, sorry, this is actually 3, 4. So this is 3, 4, 3, 5, and 3, 6. This is 4, 4, 4, 5, and 4, 6, 5, 4, 5, 5, 5, 6, 6, 4, 6, 5, and 6, 6. Okay, so these are the possible outcomes, and it says that if x denotes the absolute difference of numbers, absolute difference of numbers means we have to take the absolute values. Let's say these are the numbers. So absolute difference is 1 minus 2 is negative 1, which is 1. So this is the absolute difference. That is, if it's negative, we have to consider only the positive value. Now, the minimum difference on the pair of dice can be 0, and the maximum difference can be the difference between the maximum number and the minimum number, which is 1, which is 5. So let x be a random variable that denotes the absolute difference. Okay, so x is a random variable that denotes the absolute difference between two numbers on a pair of dice, and now x can take the value either it's 0, either it's 1, either it's 2, 3, 4, and 5. So let's find out the probabilities, respective probabilities. Now, absolute difference is 0 when we have the same numbers on the dice, and the same numbers are, these are the same numbers, which are 6. So this is absolute difference is 6 by 36. And when the absolute difference is 1, so absolute difference is 1 in these cases: 2 1, 3 2, 4 3, 5 4, 6 5, and these 1. So 1 2, 2 3, 3 4, 4 5, 5 6. And if we count these numbers, these will be in number 10. So these are 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the absolute difference when it's 1, it's on 10 favorable outcomes. So it is 10 by 36. Now 2. 2 is the difference on these numbers: 3 1, so 3 1, 4 2, 5 3, 6 4. And also it's 1 3. If we change the order, so it's 2 4, 3 5, and 6 4. And these numbers are 1 2 3 4 5 6 7 and 8. So this is 8 by 36. Now the absolute difference for 3 is on these numbers: 5 4 minus 1, 5 minus 2. So this one 5 2 and 6 3. And their receipt and their and the numbers change when we change their order. So this is 1 4, 2 5, and 3 6, which is 6. So this is 6 by 36. And similarly, it goes on decreasing. This will be 4 by 36, and for 5, it will be 2 by 36. So this is the probability distribution for the sum of absolute value of the difference of two numbers on a pair of dice. Okay, let's move on to the second part. Okay, that is the or, the B part. And for this, let's try to get some space. Okay, for part B, it's given that there are two coins. One of them is biased coin, such that the probability of the first coin is biased, and the probability of head, the ratio of probability of head to probability of tail is 1 by 3 on the biased coin. And the other is a fair coin. So one is biased and the other is a fair coin. A coin is selected at random and tossed once, and if the coin showed head, then find the probability that it is a based coin. So this question is based on Bayes theorem, and let's say this is part B. So let's say E1 be even of selecting biased and E2 be event of selecting unbiased coin. Okay, now the probability of even, because there are two coins, so selecting either of them will give us the probability half. We can select either of them out of the two coins. Now it's given that the probability for unbiased, for this is the biased coin. There is one more information for the biased coin. It's given that probability of head, the ratio of probability of head to probability of tail is 1 is to 3. And for biased coin, the probability of head, this is for unbiased coin. We all know that the probability of head or probability of tail is 1 by 2. Now, we have to get head. So head is the common event. So let A be event of getting a head on the selected coin. Okay. Now probability of getting a head if the first coin is selected. So the first coin is a bias coin, and we have total four cases here. And out of these four cases, we are getting head on the one case. So probability of head by selecting the first coin. If the first coin is selected and to get head, it will be 1 by 4. Total four cases, and we are getting 1. Out of the four cases, we are getting head on the one. Similarly, probability of getting head when the second coin is selected, it's half because it's a unbiased coin. Now, what is being asked in the question is that the head shows up, that is, head is already there, and we have to find that it was from the biased coin, that is from the even. So this is the probability that we have to find, and we are going to use Bayes theorem. So by using Bayes theorem, we get this is now probability of E1 into probability of A by E1. Same here, probability of E1 into probability of A by E1 plus probability of E2 into probability of A by 2. Let's put in the respective values. E1 is half, probability of A by E1 is 1 by 4. It's again half into 1 by 4. This is half into half. So this is 1 by 8 upon 1 by 8 plus 1 by 4, which gives us 1 by 8. LCM of 8 and 4 is 8. So this is 1 plus 2, which gives us 1 by 8 upon 3 by 8, which gets cancelled, and this is 1 by 3. So probability of getting head from the unbiased coin is 1 by 3. Okay, so this solves our question number 31, and let's move on to section D, which has long answer type questions of 5 marks each.